So let me size the audience. Who comes from a software engineering background by training? Ooh, a couple dozen people. Usually expect less. Any CLAs in the room? Good. That looks like a CLA signer. CLDs in the room? So we have more than half of the room CLAs and CLDs. Who works in teams on their projects, like 2 people or more? Good. Whose largest application in LabVIEW was like more than 5,000 VIs? What quantity? 1,000 to 5,000? Good. You came to the right room. Okay. So let's start. I'm Dmitry Sagatelyan. I come from a software engineering and computer science background. I'm a CLA and a freshly minted LabVIEW champion. I regularly present on the CLA summits, but this is my first presentation at NIWeek, so it may be toward the advanced spectrum of presentations given here, but based on the feedback, and I guess about NIWeeks, you've been asking for more advanced content, so you got it, don't complain. And again, I spent my first 20 years of profession. Yeah. Sure.
I'm sorry, I'm Nancy. I apologize for interrupting.
Yeah, well,
you know
Nancy.
We're going to have more people showing up because the Champions Lunch just finished. Would you guys kindly in the middle try to scoot towards the sides a little bit and sit next to each other, unfortunately? I'm sure we'll have a few more people. Sorry about that.
Sure. Okay. So I started my professional career working for General Physics Institute in Moscow. That's the Soviet Academy of Sciences. I was doing 20 years of system integration, real-time control systems, R&D support for world-class research in physics and basic physics. Then I came to the US and settled in the San Francisco Bay Area, joined an exceptionally good biotech company called Applied Biosystems. They were the leader those days on developing DNA sequencers, and 90% of the first human genome was sequenced using our sequencer, so that was quite an achievement. By 2009, I got tired of the corporate environment, so I started a company, Constructor Technology, and since that year, I'm a full-time LabVIEW consultant in the San Francisco Bay Area. So that's kind of my introduction. So the alternative title for this presentation is Writing Better Code Faster, which we all want to do. And by better I mean leaner and more scalable. And hopefully by the end of the day of this presentation, maybe today, because it's a long presentation, I'll show you why I think I achieved that goal. So for 25 minutes or more, I will be talking about the Agile software design principles. Then I'll talk about the monitoring system I did for a luxury vintage motor yacht, using those principles from the ground up. I'll cover the dependency injection design pattern, which is used to enable those principles, and a quick summary and Q&A. I have like 50-something slides. As I said, I cannot talk as fast as Becky, so probably I'll skip some of them. And if you have questions, fire away. If I have slides where I talk to those, will give you an answer, I'll defer the question. Okay. So when I tell somebody I'm doing Agile software design, people think it's extreme programming or Scrum or some other process. That's not the case. I don't do that. There is also the Agile Manifesto principles, the Agile Manifesto on the web. It's a great document. Follow that link. it talks about the values for Agile movement. And I find one of those values so important that I put it on the back of my business card. And it is simplicity, the art of maximizing the amount of work not done, is essential. So go there, go down the link, you'll find something very personal for yourself. Or maybe a couple. What I would be talking about is how to design code that adapts to changing requirements. That is the goal of Agile software design principle. It is based on this book. I started showing this book probably in 2013 on CLA Summits. I got my hands on it in 2011, and I'm reading it again and again and again. And every time I found something, I missed it on the other times. So, if you don't, who has this book? Ooh, 15, 20 possibly. Who read this book? 1, 2, 3, 4, 5, 6, maybe 10. Okay. So probably I would incentivize you to get your hands on it. And I have a humble goal of 20% of this room getting this book, and half of those started reading it before the New Year resolution season. And you'll do yourself a service. Okay. So I like to think about the Agile development in layers. It's easier to understand the moving parts. The top one is the philosophy, single philosophy. Then there are design principles, two groups, two related groups. The 5, the solid principles, and the package design principles. The design patterns, depending on how you count, it's 50 plus to 70 plus, and then there is a continuum of our designs and code done with the principles or without the principles. I tried to find a decent clip art for Fireway in PowerPoint. PowerPoint sucks. So I had to scan a $1 bill, and there you have it. That's part of $1 bill. And I especially like the eye because it depicts the philosophy on top. It's a never seeing every seeing guy. A slide about philosophy. This is a quote in the book. We live in a world of changing requirements, and it is our job to make sure that our software can survive those changes. This is the goal. To translate it, Uncle Bob, well, Robert Martin is known as Robert Martin. He's also known as Uncle Bob. So I'll use that name too. So to rephrase Uncle Bob, make your code as good as it needs to be at the moment, and refactor it as the requirements change. In other words, don't anticipate changes in the requirements. Most likely you would be wrong. You spend time putting anticipated code for handling anticipated stuff in your code base, and it would make your code base really, not good. And the point of the philosophy is, if you follow these principles when you build your code, the refactoring comes at incremental cost. People usually dread refactoring because it takes a lot of resources, not if you practice these principles. So in other words, Agile philosophy is continuous refactoring. The first 5 principles, if you put them in this order, they read solid. And I would refer to them as solid principles. So I'll talk about this. The other 6 are package design principles, not touching on those. John McBee, John, are you here? Yeah, that's the guy. He did a good presentation on the CLA Summit 2016. That's a link to his presentation. And John and Alan Smith also did a presentation on the topic on the Lions Day, so you may want to look for it. If you are building packages, reusable classes built into packages, like PPO, then you need those principles. The rest of you doesn't, for now at least. UML is important. Everybody can read UML. Who can read UML? Okay, I'll go through this slide. UML has a notion of dependency, and dependency means different things in different contexts. So for example, if XVI calls an abstract class A, it is a dependency, X depends on A. If class B implements an interface of class A, it extends or implements, that's a dependency. Class B uses this interface. Same thing, class C has two or more objects of class B. It depends on class B. And this is depiction of association. Yeah. And if your DVI creates and uses class C, that's composition. That's the only UML I would be using today. I would use a single example theme to talk about the principles. It is a sample scanner used for fluorescent detection, so it's most likely biotech or medical. And the sample scanner has several subsystems. It has an XY stage to move the sample plate, the Z stage to focus on the images, a camera, a light source, shutter, and a filterable cam. And usually you have a requirement, if you design a reusable component, it needs to be able to, not seamlessly, but relatively easy integrate into a bigger system. For example, we may want to add a fluidics component to increase the throughput of the entire system. So that's the example. Principle number 1, single responsibility. A class should have only one reason to change. This is kind of a no-brainer, right? Here we have a class, a monolithic scanner class, that implements the workflow, loads and saves configuration, and has methods to control all of the subsystems. This is a violation of SRP, a blatant violation. This class is not reusable. You cannot reuse the device method, and you cannot reuse the scanner itself. So the way to deal with it is break up this each class into the actual sample scanner and individual device handlers. This is kind of no-brainer, but I still see people do it this way. The next step is let's look at loading and saving configuration. I would argue that it's not the business of the sample scanner to load and save its configuration, because then you couple it to the particular storage media. Could be an INI file, a database, or something else. And if a next project, instead of an INI file, requires a database for configuration storage, your class is not reusable. So how you do it, or how I do it, I never put load and save configuration in my classes anymore. What I do, I have a constructor, and I pass a preloaded settings from the caller who knows more about the application. Then application runs, and I return them from the destructor. This is called, by the way, constructor injection. We'll talk about it later. But it makes life a lot more easy when you want to produce reusable code. This is one of the more important principles, dependency inversion. Dependency, like UML dependency. And what it says, high-level modules should not depend on low-level modules. Both should depend on abstractions. A module is a class in this case, and an abstraction is an interface. So what you do, you introduce interface classes, and scanner calls methods on those classes, and for each concrete device, you implement a class that controls that device. And this way, you decouple scanner from the implementation of device. And you can move scanner to another project and reuse it. That's kind of no-brainer too, right? Except that there are no interfaces in G. So how we do it? There is a simple way to do it. Oh, yeah, one more thing. It was also noted that the interface classes are more tightly associated with the caller than with the classes that implement interfaces. So along with dependency inversion, you have inversion of ownership. When you package and distribute your code, these interfaces should go with the scanner, because scanner depends on them. So what is the story with interfaces? We're at a huge disadvantage compared to the other languages, because we only have single inheritance. That's it. C++ has multiple inheritance. That's awful. It is better than none for some people, for some disciplined people. Java has single inheritance and interfaces. That's perfect. And Scala introduces the notion of traits. I presented it on the last summit. If you're interested in traits, I recommend you looking at the presentation. It's in the resource list. So how we do interfaces just with single inheritance? Simple way, many of you are using it, I guess. You create an interface class, which has all the methods and all the parameters. And it's an empty implementation. And you check the required descendant classes to override these dynamic display variables. That's it. That's an interface. Then you clone this class, for example, for a Sony camera, and implement the Sony camera commands. And you use a factory pattern to instantiate an object for Sony camera, and your scanner would use that object. You got Sony. If you need a different camera, like a pipe camera, you implement another class, and you inject that one. That's pretty much it. I would appreciate having an abstract method checkbox, because in other languages, when you have a class that still has some abstract methods, non-implemented methods, there is a compile error. In this case, we would receive runtime errors, which takes more time to fix. Dependency inversion principle has a second part. That's the hardest, was the hardest part to understand for me. Abstractions should not depend on details. Details should depend on abstractions. I don't know how this would be useful, right, when you're designing code. It's too abstract by itself. So this is a definition of abstraction from Uncle Bob's book. I really like it. The amplification of the essential and the elimination of the irrelevant. Still not really useful. In the next slide, I show you why it is useful and how you should use it. And in my view, this part of the dependency inversion principle, it provides guidance in how you build hierarchies of the interfaces. And there is a good example. Norm Kirchner gave this presentation multiple times, I think last time at the CLA Summit in 2015. Hardware abstraction layers. Stop writing hardware abstraction layers that stick. It's like code smells or design smells, I guess. But it was called halitosis. Yeah. So go there and look at the real-life examples. These principles, if you use it, would prevent you writing such hardware abstraction layers. So how do we design interface hierarchy? We have a sample scanner, and our goal is to make it reusable across multiple microscopes from different vendors in different configurations. So, and it has all these components, and the naive way is to create a hardware abstraction layer, get an interface for each component, and just decouple the sample scanner through an interface. Don't do it. There's a better way. You need to ask yourself what is essential for sample scanning workflow and what is irrelevant. For example, does sample scanner workflow care whether you have a tungsten bulb or multi-wave laser? It doesn't. It implements the workflow. Same thing, it doesn't care about the filter level. These are all details. What it does care about is set the color and percentage of intensity and percentage of the maximum intensity. So that should be your API. And if you want to make it reusable across multiple microscopes, you need to implement this API for this specific one, and you're done. You need only one method. You don't need to know about these details. Same thing with cameras. It would tell you, the scanner will tell you to snap an image with a certain exposure time, but it doesn't, it shouldn't care whether the image is focused or not. It should call snap, and snap would either return an error or imaging focus. So for that, you create an imager class that implements this method. And for a specific CCD camera in this page, you do autofocusing. And this would work even if you switch to an autonomous autofocus system. So this is good. And same thing with samples. Sample scanner is concerned with moving to a certain sample ID, not to an XY position on the stage. So you have a method, move to, and you introduce a class that maps sample IDs into sample plate coordinates. That's pretty much it. All you have to ask yourself what is relevant for my reusable sample scanner workflow and what is irrelevant. And then you don't get stinking hulls. In fact, I think this approach just kills the idea of hulls. You better start making measurement abstraction layers, not hardware abstraction layers. You need to go from the top, from the client. At least that's the way I do it now. Third principle, how would you do that? It depends on how you design the excitation. You may decouple it from specific hardware, yes. But that would be a really shallow abstraction layer. Yeah, you can define interfaces, but they would be hidden underneath the excitation, right? So in that sense, in the narrow sense, it may be beneficial to have the small hardware abstraction layers, yes, to decouple from vendors and from models. I agree. Open-close principle, coined by Bertrand Meyer, the father of programming language APL in 1988. And it says software entities should be open for extension but closed for modification. Let's say you have a pipe camera driver and it does synchronous snaps, blocking snaps, and you want to use that time while it exposes and integrates and reads the image to do something useful. So you decide I need an event-driven driver for the camera. And what people usually do, they add the relative event enabling private data and methods, and they have an asynchronous pipe camera code. Do not do this. Because if some other application in your company used the pipe camera code, it would most likely be broken. If not, it would have to be recompiled and retested. And we want to avoid this extra things. People don't want to depend on your current reusable module version. They want to pull in the ones they have on their schedule. So the way to do it is you define camera interface. All the green boxes are interfaces. Then you have the same base pipe synchronous implementation. And instead of editing this, you create a child of the base pipe, and you get your private data there, and your methods here. This way, this code works. It's tested. No reason to upgrade. And you got your asynchronous implementation. And it redefines the snap, so it does asynchronous snaps. And if you want a synchronous snap, you would call the parent method snap. That's it. And never ever do this. This is your road to hell. I mean software hell. Instead, use inheritance and dynamic dispatcher methodology. So this is kind of an no-brainer. But I see people do it. The fourth principle is the interface segregation principle. Clients should not be forced to depend on methods they do not use. Essentially, avoid unnecessary coupling to interfaces. This example, a high-throughput scanner has sample scanner and fluidics, and we implement a configuration handler that loads and saves the combined configuration, and methods for just getting the sample scanner config and fluidics config. This is a way to do things, but this way we couple sample scanner to the configuration handler, and It uses type definitions for the fluidics, so if we drag sample scanner to a different object, it will drag dependencies to fluidic dependencies to that object. And since those are classes, everything would be load at load time. And you wouldn't like it, right? So what we do here, you break that big interface, it's called a FAT interface, into an interface for the scanner and configuration and fluidic configuration. And as dependency inversion tells you, decouple fluidics from configuration handler that way. This should work. It works in C++ and Java and Scala. It doesn't work in LabVIEW. And the reason it doesn't work in LabVIEW is because you have this implements dependency. This means multiple inheritance. And LabVIEW does not support multiple inheritance. So I think it's a good thing it doesn't, but we need to have some other ways to have multiple interfaces. So how we can do this? There is another way to implement interfaces in LabVIEW. This is by reference interfaces. You create a wrapper class and put a camera, a DVR to a camera object, camera by value object into it. And the wrapper looks like this. This is a by value class method, and this is its interface. This is a synchronous interface. You can replace a DVR with a camera cube, and then you have a synchronous interface. Instead of doing this, you would be sending a step command here. I'm using this rarely because I hate to write wrapper classes, but on some of the classes like message brokers or global log, I have to do this. But it's a burden. It's a lot of boilerplate code. The good thing about this interface design is that these wrapper classes, the interface classes, they are stateless. The value of the DVR and camera cube do not change during their lifetime. So you can freely branch them and propagate across your application. So this is a good thing. And this approach can be used to support multiple interfaces in G. What you do instead of configuration handler implementing two interfaces, you use a facade class that wraps the same configuration handler object, but this facade class provides methods for the scanner configuration, and this facade class provides methods for the previous configuration. And since there is no inheritance, this works in LabVIEW, and it's the same wrapper. And that's how I'm doing things when I need multiple interfaces. One thing to note is once you start on this path, this is a constructor for the configuration handler. You can only talk to the handler through by reference interfaces. You need to return all the interfaces out of the constructor. If you return a by value handler class, it would be an instance of the same class but a different instance. So that's the catch. Okay, so doesn't matter. This is the last principle, Liskov substitution principle. Barbara Liskov, she is one of the few women that has there's no Nobel Prize in computer science. There is Turing Award. She's one of the people of the women that has Turing Award. And in a rephrased way, it sounds subtypes must be substitutable for their base types. Which means you define what the class does when you define the interface, the methods, the parameters, and what they do on inputs and which outputs they return. It's sometimes called a contract, interface contract. And what it says that if you create a child class to implement an interface, it should fulfill the class, the interface contract. Otherwise, you would be in a lot of pain. And I'll show you like consequences. So let's say we define a XY stage interface. And we're in the US, so it's X and Y is in inches. And we get a Lulu stage for our project. And Lulu is a German-based company. It provides a LabVIEW wrapper, but inputs are in millimeters. So that's definitely a violation of LSP. And there are consequences for breaking LSP. I'll get to them a step later. So how you fix this? Since we're in the US, we create a wrapper around the Lulu library, and we just take all the inputs, convert them to inches, and if there are outputs, we convert them from millimeters to millimeters and outputs from millimeters to inches. That's it. And instead of instantiating an object of this class, you instantiate the wrapper, and you're done. And you can do it in a couple of ways. You can do it like using the adapter pattern. It's very similar to the facade. So it holds an instance of the Lulu and just calls the wrapper. Or you can use inheritance to extend and override the dynamic dispatch methods. So design by contract is really important. There are documented catastrophic events that are known to be caused by violating LSP. I'll show you a couple of them. Okay. I need to move faster, guys. The first one is Mars climate. Oh, you don't see it. I'm sorry. The connection here is it is so slow I had to buffer the website. So Mars Climate Orbiter is a $330 million project. It was launched successfully. It took 9 months to get to Mars, and then when entering Mars' thin atmosphere, it burned down in that atmosphere. It disintegrated. When people started looking at what happened, it appears that there were two separate systems that calculate the trajectory correction. And the one provided by Lockheed outputted values in pounds of force per second. And the other one that took that input was expecting newtons per second. So they corrected the course, and the climate orbiter entered the atmosphere 100 kilometers lower than it should. That's it. Those systems are ground. They weren't scrutinized. Right? 330 million and 9 months ago. There were other problems on the team, but it doesn't matter. Okay. I want to watch this. This is Ariane 5 rocket, 1996. It's a heavy lifter. It has a payload of 3 scientific satellites, big ones, and none of those were insured. So watch what happens. It will take 30 seconds. That's the moment. I didn't hear you. And I want you to see the faces of people in the control room. I never want to get in their shoes at this moment. Give me the faces. Yeah. Okay, let's get out of this. I got one more. It's more fun, actually. But not now. No, it's a very different one. That's why I showed it. This launch costed $500 million, and still it was not insured. So what happened is there was a subsystem that was returning to the rocket main computer the axis alignment, the discrepancy between the rocket axis and the vertical, right? And that module, it takes 7 inputs, and it has all inputs as 16-bit integer, right? And the modules that feed data into it are either floating point or I64. And 4 of the inputs, they check on the input parameters and throw an exception if they ignore them if they are out of range. But 3 inputs are. And the reason is they tried to save on the CPU load. And instead of checking in real time, they did a mathematical proof that those inputs can never get out of the I16 range. But on the first launch of Atlas V, it happened. Right? So there is a really nice link here. You may want to read it. It's a post-mortem report on what went wrong by software engineers for software engineers. So you may want to read it. And what happened is that reusable module that actually caused the crash because of the overflow, it was originally designed for Ariane 4, a rocket they built like 8 years before. And nobody knew, and nobody actually knew that those parameters are not checked because there was a mathematical proof. But the rocket was different, so it had enabled different trajectories, so you got an overflow on the first launch, which actually which makes it really important, the design contract programming. If you do a reusable module, make sure there is a clear description of what the parameters are, what are the value ranges, etc. And it's better if this is enforced by a compiler, such as assert statements in ATL. In LabVIEW, for example, you can use unit tests to describe those parameters, to do the check. So you saw. I don't want to be in those shoes that I repeat. Another one, for example, your company starts saving money, and instead of Ludo, they got you a cheap XY stage. And this is a set home method. And the cheap stage doesn't support, the controller doesn't support set home. So what do? First, you can inject an error, and your sample scanner wouldn't work properly because it gets an unexpected error. It doesn't know how to handle it. It's not described in the interface content. You can ignore this situation, and things will go fine until the stage stops positioning properly, because all the incoming coordinates are in relative coordinates, right? So what you do in this case, you simulate in your software driver, your software class, the set home position. This way you fulfill the contract set by the interface class. Okay, that's not important. The last thing. I don't know if this would, if you would hear anything, but I'll try. Because I can't do as good job as I.
The code is what you call guidelines, the natural rules. The code is what you call guidelines, the natural rules.
So this is Pirates of the Caribbean and the Black Pearl. But here's a quote from Uncle Bob's book. It is a mistake to unconditionally conform to a principle just because it is a principle. which is a high-tech way of saying the same thing. So, I think that software design is still as much an art as science. Okay, let's break from the software engineering stuff. This is the project I did. This is the Acania boat. Built in 1930, 140 feet long, steel hull. Doing measurements on it is a pain, noisy, spurious currents, moves in salt water, steel hull. 300 tons displacement. It is rumored to be owned by Al Capone in the days of Prohibition. And when it was remodeled, they found a 4,000-gallon tank that wasn't connected to anything. So I suppose it was used for rum running. There are still some sheets here, guys. It was acquired by David Olson in 2008. David has a soft spot for restoring vintage cars and boats. And there was a 6-year effort to bring it up, to bring it down to the original design, replace some systems, replace the hull, do the original woodwork. It was an awesome project, and I'm really happy that I was part of it. This is the engine room, circa 1930. That's when the boat was purchased, almost from a junkyard. That's the demolition phase. You see the same engine compartment. That's how it looks now. So it has 2 propulsion Caterpillar engines, 2 gensets, and a lot of other stuff. Pilot house. This is the pilot house now. There are now 4 monitors. 2 are used by the navigation system, and I'm using these 2 monitors, 15-inch monitor for my monitoring system. This is how the hull was replaced. They brought a 3D scanner, scanned all the ribs and all the plates, took out the plates, manufactured them on the steel production, in the steel production company. Accidentally, David owns such a company in the area. So it was easy for him. Otherwise, it would cost I don't know how much money. And they replaced all the steel plates. And now, this beauty looks like this. You know, when people see it, it's just awesome. It inspires. Same thing with interior. That's the original interior. That's what it looks like now. Main dining salon. That's the new one. And of course, such a boat deserves a vintage user interface. This is 100% LabVIEW user interface. So what we did, we made some photos of the authentic gauges, and then we got the digital artists who did the digital stuff, and I just scanned the silver panel. I think it's more complicated than it should be, but it worked. This is not vector, this is pixel. If you need to adjust to other screen sizes, this would work. And this was the only requirement for the project, give us a vintage interface. And I was the only guy who knows what a computer is on the boat. So I had the liberty to build the system up from the ground using the Agile design principle. Okay, that's the boat. NI equipment is in the engine room and in the pilot house. This is what I'm talking to. 4 diesel engines from Caterpillar, 2 monitors, build sensors along the boat keel, and fuel sensors. This is the diagram. I have 3 extension chassis connected to Advantech industrial computer through an edge router behind the firewall. They have an entertainment system on the bigger network on the boat, so we don't want any interference or sharing traffic when people play movies. And a USB-enabled graphic card. This is what I was using. And I specifically used extension chassis because it simplifies the design. All the real-time actions, like filtering the messages from the engines, that's the more channel heavy part, they are done on board FPGA. So all I do is filter them on board, and then I propagate them directly to the PC. No need to have a RT controller or write RT code. This is the information flow. You have your FPGA code on extension chassis. There are data producers here for all the devices. There is some sort of a message router implemented, and then you have 3 GUIs and an event log as data consumers. This is a clean design. And you can actually say this is a model view control design because you can clearly separate these 3 parts, which makes it nice. I thought I would have time to give you a demo of the interface, but I don't. It's an extensive interface. This is the vintage look you saw. There are like 12 different views for each of the monitors, port side, port board, and starboard, because different captains want to see things differently, so they can choose from prepackaged interfaces. And there is a control interface that allows me, for example, to map interfaces into different monitors, change the color of the background for day and night, which is important, and configure the system to run in partial configurator or just run on serial. So it has some pretty good functionality. So let's get back to the. I need to read it quickly. So let's get back to the software engineering. The dependency injection principle says high-level modules should not depend on low-level modules. And creating an object is a dependency. So the question is, if the scanner doesn't create driver object for camera, stage, etc., who does? Because you first need to create an object and then you can inject it. And in this case, we're using dependency injection design pattern to do exactly that. And in software engineering speak, it is often called a container. So to use dependency injection, you need to make a conscious decision to clearly separate your application-specific code and your reusable code. So it becomes a container for reusable, for object of reusable classes. And what it does, and it's usually called an assembler class. That's the common name. There may be one or more assembler classes. What it does, it configures application-wide subsystems, like configuration, loading, saving configuration, starting the logs, starting error handling, and starting the messaging infrastructure. And then it creates, instantiates, and configures all the reusable components because it exactly knows which devices are in the system. This is application-specific code. And then it somehow injects those dependencies, those device drivers, the device object, into the composite objects like the scanner. That's the essence. This is a UML diagram. Very simple. You have assembler creating the server. That would be like a camera. Configuring it. It creates the client, the scanner, which are decoupled through an interface. And it configures it and injects the server in some way, and then it starts the client, and client does the rest. So you get dependencies that are already created and that are already configured. So your scanner doesn't need to know anything about the reusable objects you injected with. And the other benefit is that by design, reference time, the lifetime of references created here is bound to the assembler. Assembler stays in memory until the application is running, so there is no plugins coming in and coming out. And you don't get those nasty errors that the creator of your object went out of memory. There are 3 ways to do injection. The simplest is constructor injection. And what you do, you first create on your subsystem imager object, excitation object, and sample handling object, and you configure them. And then you just inject them into the scanner by passing through a connector. That's all it does. It works for 90% of use cases in my applications, and it's the simplest way to do it. Another one is setter injection, or in LabVIEW you would call Accessor injection. And it's used when your dependency objects cannot be created at the same time. So you usually create one injector per dependency, and you call them like that. The drawback, more methods, and until the last injection you got a partially initialized schema. That's not good. And then there is another way to do it. It's interface injection. It's more complicated, has very narrow use case, and it's harder to implement in LabVIEW because you need to create another interface, and we know it's boilerplate code. When you need to use it is if your camera needs, or, well, let me better say, if you implement like a resource handler, which gives away the resources for temporary use, it needs to count how many entities use it. So before doing an injection, controllers pass to the server, it does the instance counting, and then it injects itself into the cloud. I never used it, probably would never use it too. The last thing is service locators. Dependency injection is great, but a client cannot request like a new camera object when it needs it, because everything that is injected into the client just magically happens. It's not on the client's request. So there is a service locator design pattern, which is an alternative, and you need to use it when you need to swap dependency objects at runtime. There are the right ways to do it. This is an A way. You see, they are coupled here to the client and the application server locator are coupled. That is the right way to do it. So keep this in mind. This is a map. This is a class diagram of the main object of the system. You have your both specific monitoring system specific interfaces. They are reusable. You have everything that talks to the engines and builds alarms and takes other data. It's blue. It's also reusable. What may not be reusable are the UIs, because they're specific. The appearance should be specific depending on application. This part is reusable. It's reusable libraries. And what is not is the launcher UI and the Assembler Class. So in order to create a monitoring system for another board, you would need to recycle those, take it from your last project, and just apply your scales, etc., and do the changes in the GUI. That's pretty much it. I don't have time right now to show you the code. We are 1 minute to the end of the presentation, so you can download this stuff. This is very simple. This is a launcher UI. It calls the assembler constructor and standard method BringUp. It runs the system. When the system is done running, it's geared down and done. Every application looks like this, and it's a perfect place for /3. And then you have the assembler constructor, very simple too. And then this one, this BringUp method, this is a BringUp. This one starts all three GUIs together, simple. And inside each GUI, there's the constructor of the GUI, simple. And this is interconnecting all the moving pieces and using PubSub. So summary. I claim that this code base is lean, because it has 583 methods. More than half of those methods are reuse libraries, so it's only 233 for the entire application. It has only 22 application-specific classes, and has a total of 9 actors. And under the hood, there are more actors running, and it implements 156 commands. Each command in the actor framework would be a separate class. So I think 233 is pretty much lean. I talked to the slide already. And my second claim is that this is scalable. because you get a lot of reusable code and the rest you can recycle. So by using the Agile design principles from the start, what I did, I delivered a monitoring system for a specific boat, and using some extra effort, I also now have a custom boat monitoring system platform. So it's easy to switch to the next boat and do a monitoring system. These are the references. You may want to look at those. There are some really nice pieces. And the last slide, we don't have time for Q&A. Again, get this book and start reading it. I started a thread in the LabVIEW development best practices. That's the link. Please give me your feedback on this presentation. And please also ping this thread when you buy the book and when you start reading it, and share your experience with other people on this forum, because this should encourage you. Again, my humble goal is 20% of you guys getting this book, and half of those started reading it by the end of the year. And the last motivator is very visual. This is the tool you have before reading this book. This is the tool you have after. Before, after. Before, after. So I think I'm done.